Oh, hello everybody. This is the second lecture of week 8, and it's actually a very short lecture. All I'm going to look at today is the sampling distribution of the sampling variance. So basically we've already looked at the distribution of x bar, and then the distribution of x bar 1 minus x bar 2, and then the only other thing that we have to look at is the distribution of s squared, which is the sample variance. You could look at ratios of variances, but many years ago we decided to drop that out because usually you don't have enough data to really make much statements about the ratio of variances. So these are the only three things we're going to look at: x bar 1 minus x bar 2, and distribution of s squared. Okay, so as you recall, the sample variance is defined by 1 over n minus 1 times the sum from I equals 1 to n of xi minus x bar quantity squared. And again, we're assuming that the observations have not yet been taken, so these are capital X's, they are random, and that means this is capital S on the right-hand side, which is our sample variance, and it is also random. If I take a different set of observations, I'll get a different value of S squared. We saw in, I think it was last week's lectures, that the quantity chi squared subscripted by nu, which is the number of degrees of freedom, in this case the number of degrees of freedom is always the denominator used to divide the sample variance. So we have 1 over n minus 1 here. That n minus 1 is the number of degrees of freedom. So nu here is n minus 1. If we define that as multiply this equation through by n minus 1, so that this term disappears and appears on this side, and divide by the true variance, sigma x squared, so that these terms here become a sum of almost standard normals squared. Then the distribution of that sum is chi squared distributed with n minus 1 degrees of freedom, as mentioned earlier. And that chi squared distribution is non-negative by virtue of the fact that it's a sum of squared values, and it looks like this. Okay. And basically we can get values from the chi-square distribution from the last table in the summary pages. And it's an inverse table, and it gives us values along the horizontal axis with area to the right equal to the first subscript of the chi-squared variable. So chi-squared 0.95 is the point along this axis with area to the right of it at 0.95. And chi-squared 0.05 is the point along this axis with area to the right of it of 0.05. So the area between these two things is 0.9. Okay? And that 0.9 is going to lead to something we call confidence intervals. Confidence intervals being the distance from here to here, and those are standardized differences, so distances. So we'll have to turn it back into a distance in terms of the variable x itself. Okay, so let's suppose that number of degrees of freedom is 9, so that the number of terms in our sum is 10. Then from the chi-squared table, we see that this probably the chi-squared 9 lies between 3.33 and 16.92 is 0.9. And we can see that 3.33 is here, 16.92 is here. Let's go to our chi-squared table and see what areas these correspond to. So I'm going to flip over here to my summary pages. And here's my summary pages. Let's make it big. And let's go to the chi-square distribution. Okay, here's the chi-square distribution. We have 9 degrees of freedom, so we're on this line here. And we're looking for the probability that we lie between 3.33, which corresponds to an area to the right of 0.95. And what was the other one? I think it was 16.92. Let's just check that. 16.92 has area to the right of 0.5, so the area between these two has to be 0.95 minus 0.05, which is 0.90. Let's just see if I remembered it properly. This was 16.92, and this one I remember was 3.33. Okay, so let's go back to our notes, and we're looking at sampling distribution. Yeah, okay, so it's 0.9. So 3.33 has area to the right of 0.95, which is this area plus this area. and 16.92 is area to the right of 0.05, so the area between them is 0.90. Okay, so note again the chi-squared table, the t-table, and the chi-squared table are both inverse tables, so they're giving us values across the bottom for given areas to the right. So just remember that these areas are to the right. The confusion is that the standard normal table, which is the first table in the summary pages, gives us areas to the left. It's a standard cumulative distribution function. But it turns out that just because of the way subscripting works, and we don't want to carry the 1 minus stuff around too much, it's easier in the t and the chi-squared tables to give area to the right. Okay, so let's illustrate this with an example. Recall example 5.4, which is the one about the battery manufacturers who claimed that their mu x was at least 30 hours. I think that this is actually kind of wrong. They actually claimed, here, make this bigger. They actually claimed that mu x is equal to 30 hours. Let me just correct that. So I've got equal to 30 hours. Oops. Okay, that's better. A random sample of size n36, n equals 36, yielded an x bar of 27.5 hours, and we saw in the previous example that corresponded to 3 standard deviations away from the claim, in fact below the claim, and that was more than they are happy with. So they would have to go back and check to see what's going on with their batteries and why is that sample mean so low if the true mean is actually 30. The other claim was that the discovery here, if they made the additional claim that the standard deviation of the life of the battery is 3 hours, how plausible are the results of the collected sample? The original example gave us S was equal to 5 hours. This is quite a bit bigger than the claim of 3 hours. So we're a little bit suspicious that there's something wrong with the claim of 3 hours as well. So the sample variance is 25. The manufacturer claims that sigma x is 3 hours, which is sigma x squared equals 9. So now our standardization, chi-squared with the number of degrees of freedom equal to 36 minus 1, which is 35, is n minus 1 times ss squared over sigma x squared. Here we put the claimed value, which is the variance, claimed variance is 9, and sx squared is 25, n is 36, so plug in the numbers and we get 97.2 here. And we see if the claim were true about the population, if the standard deviation was actually 3 hours, then the probability of seeing a chi-squared value of 97.2 or more is the probability that chi-squared underscore 35, subscript 35, is greater than 97.2 is less than 0.005. Note our table doesn't go this high. Let's go take a look at this. So we're talking about 35 degrees of freedom, and we're looking for area to the right of 97.2. Let me just try to remember those numbers. Okay, so I'll go here. Okay, so we're looking at this table. We're going to not be able to look at things all together, but we're looking at this table for 35 degrees of freedom, so we're somewhere between these two lines. And we see we don't go up to 90, whatever it was, 97.5. We only go up to 53 or 67, so this will be about 60. So the probability that chi-squared 35 is greater than about 60 is 0.005. So that means, go back here, we can see then that the probability, where is it, 35 again, that the probability that we're less than, that we're greater than 97 is going to be even smaller. Okay, these probabilities are decreasing as we move to the right, so I would suggest that, how much are they decreasing? It's going to be quite a bit smaller. This could be I would say quite a bit less than even 0.001, which is 0.1%. Let's go back to our question here. Yes, so we see probably chi-squared 35 greater than about 60 is about 0.005. So So that basically the probability that we're greater than 97 is going to be quite a bit less than 0.005. And that means it seems unlikely that we're going to get an S squared value as high as 5 if the true standard deviation is 3. The probability of doing that is going to be quite a bit less than 0.005, so like in the order of 0.1%, which seems unlikely. So again, I would question their claim that the standard deviation is 3. And that is the end of week 8 lectures. Next week, we're going to go on to talk about basically confidence intervals. And then after that, we're going to talk about hypothesis tests. I think you'll find that this part of the course, the statistical part, is easier than the probability theory part because statistics is really more menu driven or cookbook. We have certain rules about how to compute confidence intervals or hypothesis tests, and if you follow those rules, everything seems to fall into place. Okay, so that's it for week 8. We'll see you next week. Thank you.